let's review some key features of the bony labyrinth that are relevant to vestibular therapists. There are three key regions: the cochlea, our hearing structure, the otolith organs, utricle on top and saccule on the bottom, and our three semicircular canals. The anterior canal, closest to the cochlea, the posterior canal, which you'll notice is at about a right angle to the anterior canal, and then the horizontal canal, which is perpendicular to them. So the horizontal canal is the most lateral structure within the inner ear. Hence, this is a left ear model. So if this were inside my ear, it would be pitched back about 30 degrees. So the horizontal canals are about 30 degrees pitched back from the horizontal plane. So to get them in alignment with horizontal, I'd actually have to tip my head forward about 30 degrees. So inside this bony labyrinth is housed a membranous labyrinth. And that's why on the model you'll see the inside looks gray. That's meant to represent the membranous labyrinth inside. The other thing that probably sticks out here is the endolymphatic stack, which produces our endolymph, and the endolymphatic duct connected to it. Next up, we have our nerve supply. So cranial nerve 8, the vestibulocochlear nerve, is what supplies the inner ear. You'll notice a cochlear portion here supplying the cochlea for hearing, and a vestibular portion supplying our entire vestibular apparatus for our sense of balance, our ability to detect angular acceleration of the head, static head tilt, and linear accelerations of the head. So that vestibular portion of the nerve is divided into two sections. There's an inferior portion, which is only traveling to our posterior canal and our saccule. The superior portion of that nerve, the superior portion, is traveling to the utricle and our horizontal canal and our anterior canal. Now you'll notice on my model that there is a tumor. So commonly, the most common kind of tumor to have in here, a vestibular neuroma, vestibular schwannoma, acoustic neuroma are some names of tumors that can occur on the vestibulocochlear nerve. So this tumor here is meant to represent that, and in this case, the tumor so far is only affecting the vestibular portion. The other key feature that we haven't talked about on this model is that for each of the semicircular canals, so this one being the anterior, there is this dilated end. So each canal has one dilated end. The ampulla, seen here for the anterior canal, seen here for the horizontal canal, and seen here for the posterior canal. So this one was our left ear. This one is our right. So for that right ear, you remember the cochlea was more medial, right? The anterior canal is closest to the cochlea. The horizontal canal is our most lateral structure. And the posterior canal is in the back, and it's at about a right angle to the anterior canal. Remember that in my ear, the horizontal canals will be pitched back about 30 degrees. So to bring them level with the horizontal plane, I would have to pitch my head down about 30 degrees. Remember also that these structures in real life would fit on the head of a dime, so super tiny. So we're using enlarged versions of them to understand the relationships amongst these anatomical parts. So we did paper models earlier in the week, and you can see here that the horizontal canal is like the floor. The anterior canal I have out in front, this is a right ear, and the posterior canal in the back. So if this were a right ear, I would be pitched back a bit, but horizontal canal is the floor, and anterior and posterior are going to make the walls of our paper model. And you're going to notice that these relationships amongst these canals is the same in my larger model. So you can use the paper model to kind of understand these different relationships. Likewise, we made a pipe cleaner model of the semicircular canals. So with this one, you can also see some of those same relationships amongst the canals, that the horizontal is going to be our lateral structure, and that the anterior and posterior canals, mine got bent a little bit, but they're meant to be at about right angles to each other. So the red and the green here. And you'll notice on your pipe cleaner model, we have a little ring, and the purpose of the ring is going to be to show what happens with displaced otoconia from the utricle. What happens if they end up in the posterior semicircular canal, which is the most common scenario for BPPV. On our larger model here, we have a green ring representing loose otoconial debris. Normally this would be within the semicircular canal. It's not on the outside like you see with the rings here, but it provides a good visual for you to be able to understand where the otoconia would be during a canaleth repositioning maneuver. Essentially what we're trying to do with canaleth repositioning maneuvers is to get these particles back into the utricle. And for the posterior canal, in order to do that, we're going to have to go around that entire hoop and then through the common crus, this area here, in order to get the particles back into the utricle. So our next video will focus on how we do that.